Hello, my name is Catherine Mimnaugh, and I'm a doctoral student in the Perception Engineering group at the University of Oulu in Finland. I'd like to thank my collaborators in Finland, the US, and Mexico for their assistance with this project. I suspect that you're interested in ISMAR because of your passion for AR, VR, or XR, and like me, you want to help these technologies be more enjoyable or effective for any number of different applications. But as you know, there can be side effects from using these technologies. Cyber sickness. I will refer to these uncomfortable symptoms as VR sickness here because I used a virtual reality head-mounted display in this study. So why should we, as developers and researchers of these technologies, study the effects of VR sickness on the user? Well, for starters, although there's been a lot of research on what contributes to VR sickness, not as much research has been done on what it means when sickness is occurring. This is a problem because a significant portion of the population is susceptible. And if we have a better understanding, then we can make more informed decisions when choosing options that may affect VR sickness in our applications, like the type of locomotion. In many applications, it's desirable that users can fully engage with the content, which may not occur if cognitive function is impaired. Furthermore, any cognitive impairment due to VR sickness may have performance impacts as well. The idea for this study came from the intuition that as sickness develops, it may become more and more of a distraction from whatever you're trying to do in VR. Fortunately, there are ways to measure changes in attention during VR. One of these is through a pattern of brain activity called the P3B. The P3B is captured through electroencephalography, or EEG. EEG involves placing sensors on the scalp to record the electrical signals that are generated when neurons in the brain are firing, as you can see from one of the study participants here. The P3B is an event-related potential, which is a type of neural activity that occurs after a certain type of stimulus. In this study, we elicited the P3B by having subjects listen to a particular series of beeps. The series consisted of more frequent lower tone beeps, called the standards, that occurred about 70% of the time. Interspersed were the higher tone, infrequent beeps, called the oddballs, that occurred about 30% of the time. It sounded something like this. While the beeps were playing, subjects were asked to keep a silent count of how many of the infrequent oddball beeps occurred. In a previous experiment, we tested how certain types of movement through this virtual museum affected VR sickness. From that work, we had one path through the museum that moved in straight lines with only two 90-degree turns, which we knew caused a mild amount of VR sickness. The other path was circuitous and made many small and large degree turns, which we knew caused a higher amount of VR sickness. In this study, 29 participants listened to the series of beeps that elicited the P3B while they were taking these paths through the museum. The low and high sickness paths were both repeated. Subjects also listened to the P3B beeps outside of VR at the beginning and end of the experiment and in VR without any movement. When the subjects listened to just the beeps, it was called a single task block, and when the subjects listened to the beeps while in VR, it was called a dual task block. This is what a P3B effect waveform looks like, which is created by subtracting the brain activity after the frequent standard beeps from the brain activity after the infrequent oddball beeps. For this presentation, I've added a 10 Hz filter to the waveforms for display purposes only. On the vertical axis is the amplitude of the signal in microvolts. For historical reasons, negative amplitudes are plotted up. On the horizontal axis is time. 0 is the point at which each beep sounded, and the 200 milliseconds before the beep served as baseline. We computed the mean amplitude of the P3B from 250 milliseconds to 450 milliseconds after the beeps sounded based on prior literature. These waveforms are a grand average, which means that they're the average from all 29 subjects after 114 beeps per block. So they're essentially one line representing the average of the brain activity that occurred during a particular condition. The P3B has been used in brain research for 50 years and has been shown to reflect attentional allocation. You can think of attention as a pool of resources that many different cognitive processes draw from. So let's say this is you, and we're measuring your brain waves while you're listening to the beeps as a single task. Some attention would be dedicated to listening to the beeps, but your pool of leftover attentional resources, called attentional reserve, would be pretty full because you only need to focus on one thing. Your P3B might be pretty big and look something like this. So now let's say that you're also in VR, making this a dual task. More attention will be directed to doing two things, So attention is taken away from the reserve and your P3B would get smaller. But what if you start feeling VR sickness? If these uncomfortable symptoms take up some of your attention, then more resources are taken away from the pool and the P3B will get even smaller. But if VR sickness was not capturing attention, then the amplitude of the P3B would not change. So what did we find? The first dual task was in VR, but the subject sat stationary at the beginning of the museum, which gave us a dual task baseline. We measured VR sickness with a questionnaire that subjects completed after each block, the Simulator Sickness Questionnaire, or SSQ. Here you can see our average SSQ total scores during the baseline, and here's the no sickness waveform with the P3B. Next was our first low sickness block when subjects began moving through the virtual museum. The SSQ scores increased a bit, but not a statistically significant amount. Yet when we look at the waveforms, there was a significant decrease in the P3B effect mean amplitudes. Then we had our first high sickness block. This time, the increase in SSQ scores from baseline was significant. The P3B amplitudes during the first high sickness block were significantly reduced compared to the baseline, but they were not significantly reduced compared to the low sickness block. Our fourth dual task was the second low sickness block. SSQ scores were not significantly different from baseline or from the high sickness block, and the same was true for the P3B. As you can see, there was not much difference in amplitudes in our window of interest. Our final dual task was the second high sickness block. Like the first high sickness block, the SSQ scores were significantly greater than baseline, and there was a significant decrease in P3B amplitudes from the first low sickness block to the second high sickness block, potentially showing the cumulative effects of the sickness building across exposure time. But you might wonder if it was just being in VR, the motion through the museum, or the museum itself that captured attention, and not specifically VR sickness. The P3B is sensitive to cognitive load, so we wanted to test if our reductions in the effect mean amplitudes were specifically related to VR sickness. So we used hierarchical linear modeling to examine the relationship between P3B amplitudes and SSQ scores. Here you can see the relationship between self-reported VR sickness symptom severity and the effect mean amplitudes of the P3B. As you can see, there was a significant relationship such that the increase in sickness scores was associated with a decrease in the P3B amplitudes. This association is really interesting because it shows that how people reported they were feeling was in fact had some relationship with changes that occurred in their brain activity. The association grew stronger as the study progressed. Furthermore, this relationship between SSQ scores and the amplitudes of the P3B held regardless of when in the study the sickness occurred. Additionally, we found that gender, previous VR use, and computer gaming use did not improve model fit and thus did not account for a meaningful amount of the variance. As you may remember, subjects had to count how many infrequent oddball beeps occurred. We analyzed how accurate they were in their beep counting and found a relationship between how much VR sickness they experienced and how accurate they were in counting, which is mediated by the P3B amplitudes. So as VR sickness increased, P3B amplitudes decreased, and as P3B amplitudes decreased, the number of errors in the counting task increased. So what does it all mean? Well, first we've shown that there is a relationship between VR sickness and attention, such that VR sickness may draw attention away from immersive experiences. Second, we found that VR sickness had a detrimental impact on task performance. And finally, this work introduces a method that could be used with other immersive experiences to track cyber sickness as it is happening without asking participants to continuously report how they're feeling. So it could be used to compare how sickening certain aspects of other immersive experiences are. Thank you for your attention. I'd like to thank these people and these funders. I'd also like to mention that all the materials from the study and the subject data are available online. Thank you.